coil or a smaller dedicated wrist coil, something that fits the body part. Not that the body part is going to get lost in, okay? So the type of receive coil that we choose has a lot to do with our signal. Okay, so breaking these down again, proton density. More protons in the sample yield a higher signal. Fewer protons will yield a decreased signal. Example, brain tissue versus lung tissue. Somebody break that down for me. Where would I get more signal, brain tissue or lung tissue?
Brain.
Why?
Lung is full of air.
What are the lungs? They're air, right? What's in the brain tissue?
Fat.
You've got, right, they're different, there's more density in the brain tissue. You've got fat, you've got fluid, right? You've got brain tissue. You're not looking at just air, okay? So, again, and then fat versus cortical bone. These are, when you're dealing with fat, what do you have for fat? It's all, what? Either all bright. When is fat bright? Very good. When is fat dark? That was easy. Okay, so depending on the body part that we're doing, if we want to get more signal, body parts that have more proton density, like brain tissue, will yield higher signal. That makes sense? All right, so let's break down our voxels here. Voxel, the volume directly affects the amount of proton in each pixel. How is that? Determined by slice thickness, your field of view, and your matrix. How does our slice thickness affect signal? Do I get more signal from a thicker slice or a thinner slice? A thicker slice. Because think about it. If you're doing, how many of you guys can see when your signal, when you lose signal, when you change a parameter? On the G, it's on the bottom of the screen. If you change a parameter, it will tell you, let's say, every protocol that gets saved, when you open it up and you start using it, whatever parameters are set there will come up at 100%. Does that mean that that is 100%, 100%? No. It means when it was saved in good faith that this is good. Okay? So I always caution people, you can save a shitty protocol. That's a real quick one. The parameters are not conducive to high signal. But when you pull that protocol up again, it's going to come up at 100% because the system thinks, because you saved me, I'm in. I'm the top dog, okay? So when you start out with a protocol, at the bottom it's going to say relative, on a GE, sorry guys, it'll say relative signal 100%. If I have a 5 millimeter slice thickness, and I change my slice thickness from 5 millimeters to 3 millimeters, I'm going to immediately see a decrease in signal. Okay? So to achieve more signal or higher signal, we want a thicker slice. We want to choose a thicker slice. Does a thicker slice always mean better? No. When do we want a thinner slice?
For smaller parts.
Smaller body parts. Okay? So I'm not going to use the same slice thickness that I do for full axial of the brain when I go and I do the IACs or the orbits or the pituitary because it's a smaller structure. So if I'm using 5 millimeter slices, I may only get 3 or 4 slices through that area with a 5 millimeter slice. Does that make sense? So we use a thinner slice to cover smaller anatomy or smaller structures. But What happens is when you go from a 5 millimeter to a 3 millimeter, you're going to lose signal. So that's where we have to know what to adjust, where to adjust. Now, on your systems, the protocols are saved in good faith at 100%. And you know what? They pretty much all are, okay? But it's very easy to save a protocol, and when you get it, it's not a good protocol, and you open it up and it says, I'm just letting you guys know that you open it up and it says 100%. But the ones that are saved on all the systems that we're all using, 99.9%, you know, they were saved, and they're good ones. So you can, when you open up the Orbit protocol, it's already going to be at a 3 millimeter. You're not going to have to change it. But I do want you guys to know, if you are scanning at a site, let's say, and you see something and you call the radiologist, hey, you know, I see something in the pancreas here. And the radiologist says, you know, you're using 7 millimeter slices. And he says, we'll do 3s through the pancreas. Know that just to go in there and just change it from 7 to 3, you're more than halving your slice thickness. So you're going to lose a lot of signal. Okay? So the best scenario there is, if you're in a protocol, just the regular abdomen, let's say, you're doing 7 millimeter slice thickness, you see something, you call the radiologist, and the radiologist says do 3s, what should you do? I'm going to give you something much easier to do. Go back into your protocol. It's already set up for 3 millimeter slices. Okay, that's the easy way. But when you're sitting there and you're in that position, you're thinking, and then you look at your signal, and your signal goes from 100% down to 60%, and you're like, great. So now, next thing you know, you've got, instead of a 15-second breath hold, you've got a 45-second breath hold because you're jacking this up, you're jacking that up. The first thing I want you guys to do is go back into your protocol. Because I'm sure that in there somewhere, there's something saved for 3 millimeter slice. That's a little cheat. I gave you guys a little cheat there, okay? But in retrospect, if you're going to go from a 7 millimeter to a 3 millimeter, you have to adjust. And those adjustments are going to cost, they're going to cost you. No matter what. You're never going to take that 3 minute, 7 millimeter scan down to a 3 millimeter, still at 3 minutes. It's going to increase. I'm just know that. But if you're out there and this happens to you, first thing you should do is go into your protocols and look for something that's already saved at a 3 millimeter. Okay? All right, so slice thickness. Field of view. How does field of view affect our signal? Directly. So what does that mean? Absolutely. And we're going to learn how much it increases. Field of view and NEX are your biggest signal increasers. Okay? One's going to cost you time, and the other one's not. Which one's going to cost you time? Your NEX. Your field of view is not going to cost you any time, but you're going to lose. You're going to lose. No, if you make your field of view from 24 to 26, you raise it, you increase it, you're going to increase your signal. However, what's going to happen to your image? Your image is going to go smaller. Okay, so we start at a 24, right? We want to get some more signal, we make it to a 26. Okay? You're going to get some more signal, but you're going to lose some resolution, your image is going to get smaller. Okay? Your matrix. How does our matrix affect the signal? A fine matrix will give us less signal. A coarse matrix will increase our signal because with a coarse matrix, the pixels get bigger. You have less pixels in that field of view, gives you more signal. The higher or finer matrix, the higher numbers, you have less pixels in there. It will decrease your signal, but it will increase your resolution. All right. So when we view images, remember, voxels are 3D, and they're represented as pixels, which are 2D. Voxels are 3D, pixels are 2D. All right, so if we want to figure out voxel volume, which the only time we ever need to figure out voxel volume is when we are doing our scans for the ACR. The ACR has set guidelines that our voxel volume has to be certain sizes and stuff. So in order to figure out or calculate our voxel volume, we're going to take our pixel phase dimension times frequency times slice thickness. So what does that mean? If you have a 24 field of view, you're using a 256 by 228. 256, what number is that?
Frequency.
Frequency. 128 is our phase. Remember, frequency is always the first number. Even though we always say, we always say phase and frequency. And then we have a 3 millimeter slice. We're going to take that the 24 field of view is in centimeters. So that's, the GE uses 24. I know that Philips and Siemens use the 240. They put this there, they use it in millimeters. So you're going to convert your 24 field of view from centimeters to millimeters. So if you see 24, that's always centimeter. So you're going to make it to millimeters. So you're going to take 240, you're going to divide it by the frequency matrix. Then you're going to take the field of view again, divide it by the phase matrix. So you're going to do this division, multiply this times this, and then times the slice thickness. And that will compute out to your voxel volume in millimeters cubed. So again, this number here, the 24 field of view, you always want to convert it to millimeters, make it 240. Take your field of view, divide it by your phase matrix, take your field of view, divide it by your frequency matrix, multiply those two, and then multiply this, once you get this answer here, you're going to multiply it by the slice thickness. That'll get your voxel volume. Okay? That will be on the boards, how to figure out voxel volume, so make sure you guys know that. What? Your matrix. Your matrix is your frequency and your phase. Yeah. Your frequency being the higher number, your phase being the second number. So you're going to take your field of view and convert it to millimeters, because this here is centimeters. You're going to divide it by your frequency matrix. You're going to take your field of view again, divide it by your phase matrix, multiply this answer by this answer, or multiply this times this, and then multiply it again times your slice thickness. Okay? And your answer is going to come out into millimeters cubed. Is everybody good with that? Okay. Slice thickness. It has a direct effect on your signal to noise. If you double slice thickness, it doubles your voxel volume. Hence, if you half your slice thickness, you're going to half your voxel volume. So if you double your voxel volume, right there, with doubling your slice thickness, you are directly affecting your signal by increasing it. Okay? But again, that's not a parameter that we're going to throw around loosely, except for this one over here. She's going to cheat, and she's going to change her thickness. Typically, you don't touch that. Usually when you do touch that, it's going from a thicker to a thinner. in order to cover a smaller structure of anatomy, okay? Okay, so changing the field of view alters the anatomy, obviously, covered in both the phase and frequency directions. It's what they call a squared relationship. If you double the field of view, you will increase your signal by 4. This also is on the boards, okay? Double your field of view, you increase your signal by 4 times. When would I go from a 20 field of view to a 40 field of view? Big head. Okay, theoretically, this is what happens if you double your field of view. Would I ever double my field of view? To get more signal? No. But this is what happens. So if you cut your field of view in half, your signal decreases by 4. So I guess think about it that way. Let's say you go from a 20 to a 10. 20 field of view to a 10 field of view. That's halving it, right? That's not a big stretch like going from 40 to 20. But theoretically, it's the same thing. Would we ever really do that? No. I would never double my field of view. Unless, of course, I had to cover more anatomy. That's the only time I would.
The patient's not going to fit anymore.
There you go, that's right. Yeah, I had a patient today where the one girl that I work with, she's like, actually, she's not going to fit. She fit. She definitely fit. But anyway, you're not going to double it behind the scanner, trust me. Theory, double your field of view, you're going to increase your signal by 4. Half your field of view, you're going to decrease your signal by a factor of 4. Field of view has a large impact on signal to noise. So again, if you're really desperate to get some signal, maybe 1 or 2 clicks up on your field of view from 24 to 26. It's not going to double it, that's for sure, but it's going to give you a little bit of, it's not going to impact as much as if you double it. Make sense? Okay. Your matrix. Coarse matrix, 128 by 128. That's a small number of phase encodings and a small number of frequency encoding. Remember, you take that field of view. If I'm using 128 by 128, I'm fitting less pixels in there, makes the pixel size bigger, so it increases. Your fine matrix is a 512 by 512, which is a high number of frequency encoding, a high number of phase encoding. We want to use this one for signal, correct? And this one for resolution. Okay? So here's just an example. I think I've had this slide, showed this slide to you guys before. There's your 128 by 128. There's the size of your pixels. Take your frequency matrix and double it. Change it to 128 by 256. You lose half of your signal. See the size of your pixels here? Now, double up your frequency encoding. So now you have a 256 by 256, or square voxels. Your signal goes down to 0.35. Okay? However, with this small size pixel, we're going to get more detail, more resolution. Okay, but when it comes to signal, you want a coarse matrix so that the pixels are bigger. This has an indirect effect on signal. So your coarse matrix, decreased matrix, increases voxel size, more signal. Your fine matrix, increase your matrix, you get smaller voxels and less signal. It's all a trade-off. Pulse sequences. We've already talked about spin echo and gradient echo. Why do we have more signal for spin echo? Because is that 180 rephasing is going to help to clean up all those inhomogeneities, clean up the crap, okay? Make a much better image. The gradient echo cannot compensate for those inhomogeneities because the gradient that gets used for rephasing cannot clean that up and does not push them past the transverse plane. So here's a perfect example. If a patient has metal, what pulse sequence do we not do? A gradient echo. So here's your gradient echo. Patient's got some metal in the knee. There's your spin echo. See how much cleaner it is compared to the gradient echo. Okay? So always remember that a spin echo pulse sequence will always generate more signal than a gradient echo. The RF is more effective at rephasing spins in the transverse plane. Yields increased signal in spin echo compared to gradient echo. Timing parameters, TR. Long TR allows for more longitudinal recovery. This means more of the NMD obviously will make it to the transverse plane, okay? Larger transverse magnetization equals larger signal, higher signal, okay? What is the NMD?
Magnetization vector.
And where do we get that from? Where does it come? What is it? It's the signal that's given off by the patient, right? What controls the NMD? Strength of the magnet, very good. So we really can't control that per se, but a higher magnetic field or greater magnetic field will yield more NMD from the patient. So longer TR will equal a higher signal to noise. However, what do we have to be careful of? Right, TR controls T1, so we have to be careful there what we want to achieve. If we want to achieve a T1 weighted image, we want to make sure that our TR is in line or short. Your TE. Short TE is going to prevent decay of the transverse magnetization. Larger transverse, obviously, magnetization equals higher signal. Shorter TE equals higher signal. How are we doing with the parameters? We went over them all before class, right? Before we started and this is just kind of bringing it home. Everybody's good with it? All right, so number of excitations or number of signals average determines how many times each phase encoding is repeated. Why is phase encoding important?
More information.
Why is phase encoding important? Where does all the data go that we collect? K-space. How do we fill K-space?
With the phase encoding data.
Oh, every time phase encoding is done, a line of K-space gets filled?
Every time a TR is performed, a line of K-space is filled. However, what has to change in order to fill different lines of K-space? What, Jen?
The slope, the
Slope of the phase encoding. Remember? If we don't change the slope of the phase encoding, the same line of K-space will get filled. When is an image complete? When all the lines of K-space are filled. Right? Coming back? Okay. So the next determines how many times each phase encoding step is repeated. So for one NEX or one NSA, one number of signals average, one excitation, each line of K-space is filled one time. So if we go to 2, each line gets filled twice. Does that make sense? So the more times that that line of K-space gets filled, the higher the signal, the higher signal to noise, what happens to our time? It increases. So again, we have to be really careful there, but the NEX is what determines how many times that the line of K-space gets filled, or the number of phase encodings that get repeated. If the phase encoding slope remains the same, then the same line of K-space gets filled. So signal versus noise and NEX. Again, noise occurs randomly. Okay, it's going to occur on every single sequence you do. But signal is reproducible. Okay, we know how to get our signal. We know what parameters to use to increase our signal. Each time a line of K-space is repeated, the signal is the same and the noise is a little bit different. Okay, sometimes it may be a little less noise, sometimes it might be just a little bit more. So if we double our NEX, we increase our signal by a factor of 1.4, or the square root of 2. So all these little numbers here are really important for the boards. We double our field of view, what happens to our signal?
4 times.
We increase it by 4. If we double our NEX, we increase our signal by a factor of 1.4, or the square root of 2. So if we go from a 1 NEX to a 2 NEX, we are not essentially doubling our signal. You see what I mean? We're going to do it by a factor of 1.4. However, if we doubled our field of view,
4 times.
right, we would multiply it by 4. But again, I don't need to double our field of view. Not going to happen. Okay? So, this is a little bit more, or a lot more realistic to do to increase your signal. Going from a 1 to a 2, yeah, you're going to get 1.4 times the signal. If you go from a 2 to a 3, what are you going to get? You're going to increase your signal by 0.7, right? Right? 1 to 2 is doubling. 2 to 3, we're not quite doubling. Okay, so we're not going to double our signal by going from 2 to 3. We will increase signal, but the main objective here is doubling NEX will increase our signal by a factor of 1.4. That is also on the board.
So this one is saying that the mix doesn't affect the signal at all.
No, that's not what I said.
It does.
Doubling the NEX will increase our signal by a factor of 1.4.
Well, it says each time a line of K-space is repeated, the signal is the same. And
The signal is the signal is the same, but noise is a little bit different. So if you want to increase your signal by using your NEX, you can double your NEX and it will increase your signal. When you increase your signal, it's going to get rid of some of that noise. So basically what I'm telling you guys to do here is if you need more signal, you're better off using your NEX to gain signal. Because if you double it, you're going to increase your signal by a factor of 1.4. When you increase your signal, it will help to soften that noise. So each time a line of K-space is repeated, the signal is always the same, but the noise is a little bit different. It might be more on one line, it might be a little less on the next, it might be a little more on the next. And noise is never reproduce exactly each time. Signal is.
Oh, that's the same.
Okay? Does that make sense? Does that make more sense? Signal is always the same, but the noise is going to be a little bit different.
But it doesn't worth it that if you increase the next for like 2 times or 3 times because you get more noises. So.
No. The more signal that you reproduce or that you produce, it's going to soften that noise and get rid of that noise. Okay? But again, if you just did, let's say, 1 sample, each time that line of K space is sampled, the noise is a little bit different. It might be, you might have more noise on this line, less on this one, less on that one, more on that one. So what we're saying here is you can use nets to increase your signal, which will help to bring down that noise. Okay? Increase your signal. Doubling your signal will increase, doubling your nets will increase your signal by a factor of 1.4. You're welcome. Receive bandwidth. What are the 2 bandwidths that we have?
Receive and transmit.
What is the difference? Which one's tech control? How is the transmit bandwidth controlled?
Changing the slope.
Slice thickness?
And the slope.
Something between
No. The steepness of the slope. Okay? How do we control transmit bandwidth? Basically by changing our thickness. By changing the slice thickness, we'll change the transmit bandwidth, but it's nothing that we actually go in there and do. When we change the thickness, it changes the transmit bandwidth and the slope, the steepness of the slope. Okay? So, again, noise occurs in all frequencies. The receive bandwidth will determine the range of frequencies during our readout, both signal and noise. So, Brittany, I'm going to throw this back at you. You said earlier that receive bandwidth was one of the parameters that you see being manipulated. And you said when you do see it get manipulated, it's because of metal. And what do they do with it? Okay, so when metal is present, what happens? You get a lot of noise, right? You get artifact, you get noise. So if you increase your receive bandwidth, you're increasing the range of frequencies that are being sampled. Okay?